we're going to talk about how to execute a recursive function in MIPS. So right here we've got the Java implementation of a function that takes in an array of integers and its size and returns the sum of all the elements in the array. So our strategy here is going to be that the base case is when the size of the array is 0. Our inductive step will be to add the last element of the array to the sum of the first size minus 1 elements of the array. We translated this function to MIPS code. That's right here in this box, and down here in this box is the code that's going to call the sum function. So right here we've got the data section just so that we have an easy way of defining an array of 3 elements to test the function out. So 1, 2, 3. This is the address where that array starts, and in the text section is where we put our code. Remember that in MIPS our function arguments go the first argument in A0, second argument in A1, and so forth. We see that sum, we want it to have 2 arguments. We're going to use A0 for the address of the array, and then we have the size here. So that size is going to go in A1. Size is 3 here for the size of this array. Then we go down to jal sum. Remember what jal does is it's a function call. It has 2 steps. First, it's going to store PC plus 4 into the return address register, the RA register. So actually, we've already written that in here. Why is that important? Well, eventually, the code that we're calling needs to know how to get back to the line after we called the function. So we need to store this address so we know where to go. Do the second step of jal, which is to jump to this label. Here we're going to push 2 things on the stack, S0's value and RA's value. Why S0? Because we're going to overwrite it. We're going to overwrite it somewhere in the function body, and S registers have to be saved so that the caller is expecting to have whatever value was originally there, so we better make sure that's the case. We have to save RA because we're going to overwrite it when we call jal inside of here, and we need to keep around the old value. Stack pointer -8. Right now the stack pointer is 400, so it's pointing to this spot in the stack, and we need to subtract 8 from it. So now it's right here. We're storing the value of S0 at that address. Put a question mark. It actually doesn't matter. Turns out nobody was using S0, so this should go at the stack pointer address, which is 3F8. And then at an offset of 4 from that address, plus 4, we're putting the return address. Return address is 80C, so that's going to go right here. Now we check, is A1 equal to 0? Nope, so we'll keep going. We're going to calculate the address of array size -1 with these 3 lines of code. You can take a look at that closely and convince yourself that's the case. Then we're going to read the size -1th element of the array, put it in S0. We're going to make our recursive call to sum. It looks like this in the Java code. So notice that the first argument is exactly the same as how it was called for this call. The second argument is just -1 from what it was. A0 already has the right answer in it, and now we just need to change A1 to subtract 1 from it, and then we can call sum here. So let's make sure we keep track of all these registers that we've been changing. This is 2 right now. Now we have to execute this jal, so we save PC plus 4, which is this address, into the return address register, 728. Okay, so notice already this is important. We overwrote this value, this original value. Eventually we're going to have to get back here, and that's why it's very important that we've saved the old value here in the stack, because we're going to need that later. So the second part of jal is to jump to the label, and now we're starting the whole process over again. We just have slightly different arguments this time. So we're going to change the stack pointer. Now it's pointing here. We're going to save S0 and RA. Then we check, is A1 equal to 0? No, not yet. We are getting the last value of the array, which now we think the array is 1 element smaller, so we'll be putting a 2 in the S0 register. We'll update the A1 argument because we're going to get ready to make that recursive call. And we make the call. So we have to store PC plus 4 to the RA register. It's already there, so let's just not overwrite it. And we have to jump to the sum label. And now we execute this again, change the stack pointer, save S0 and RA to the stack. Execute all this stuff again. We're going to get the first element in the array into S0. We'll update our A1 argument, our size, and we'll call sum again. So store PC plus 4 into the RA register. Got it there already. Now jump to the sum label, push these two things on the stack. So it's going to go here. RA's value is going to go here. And now A1 is being checked against 0. A1 is now 0. So we're going to jump to our base case. So now we're executing this part of the algorithm. So base case is down here. We are doing something to V0. Now remember, V0 is the designated register where you put the return value of a function. So here the return value in the base case is supposed to be 0. So let's put the value 0 in register V0. And now we'll continue executing. We've gotten to here, and what we're doing is reversing the process of managing the stack. So now, because we're returning from the function finally, we have to start taking stuff off the stack to get back those old values of S0 and RA. So first we're taking what's in the current stack pointer's position. We're at 3E0, so right here. Take what's at that position and put it in S0, save it here. Put what's in the position plus 4 from the stack pointer, so that's here. Put that into here. And JR, we have to add 8 to the stack pointer. Now we're right here and we can use jump register on the RA register. So what this means is just take the value in that register, so 728, and jump to it. We're jumping here. Okay, why are we jumping here? Well, remember the whole point of saving the return address when you called gel was so that you can know how to get back to the line after the gel when you return from this function call. So that's why we ended up here. And now, where are we relative to the code? Well, we've returned from our call, and we have to still add the return result we got from the function to the last element of the array. So remember, we actually saved the last element of the array into S0. So it's actually pretty cool that we could use the S0 register for this, because S0 is a saved register. It should be the same before and after the function call. So that's why we used an S register there. So you can see we're going to do this operation. The other cool thing is that V0 is our return value register, so we should expect that the return value of this call is in V0. Of course, we made sure that was the case because we set our V0 register. So now we'll update S0 with 1 plus 0, it's 1, so it's still 1. And we're putting the value into V0, because remember, now we have to return this calculation. So we need to update our return value with that sum. And now we're jumping to some end. Why are we doing this jump? Well, we just need to make sure we skip over some of this code. That's common anytime you have an if statement, because you only want to execute one of the cases. So we're jumping down to the end where we return from the function by cleaning up the stack. So now we load whatever's at the stack pointer 2 into S0, and we load whatever at plus 4 into RA. So it's still the same value. Now we're adding 8 to the stack pointer. And now we're jumping to the RA value. So it's 728. So we jump here. Now we're adding V0 and S0 and putting it in S0. So that's 1 plus 2. We get 3. We're copying that from here to here. So that's us setting our new return value. And now we're jumping to the end of the function, doing our stack thing. So right now the stack pointer is F0. So we're taking what's there and putting it in S0. We're taking what's in the plus 4 offset and putting it in RA. RA's value, 728. We need to add 8 to the stack pointer. And then we'll jump to 728. We will add S0 to V0, and we'll move that value into V0 and jump to some end. So we go here, and we are loading whatever's at the current stack pointer into S0, loading whatever's at plus 4 from here, so that's here, into RA. Aha! we finally have a different value. And we are adding 8 to the stack pointer. And we are jumping to whatever's in RA. And RA is 80C. So let's find that. 80C right here. Great. So now we have finally returned from the sum function. And what are we ultimately looking for? Well, we're looking for the return value from that function. So we're looking at v0. And in fact, v0 has the right answer, 6. 1 plus 2 plus 3. All right, so just to sum this up, notice that this stack, even though it contained a lot of the same values sometimes, especially for RA, what mattered was that it contained that many values for the number of times that we had to return from recursive calls to the sum function. So, and then at the very top, we had the original person who called us so that we could get back to the caller. The other thing is we made sure to set our arguments before we make our recursive calls. So right here, we had to set it to size -1, so we're always subtracting 1 from the current size. We just never ended up changing A0 because it was always the same value, as you can see here. Array, array. We put the return value into v0 before we return from the function. So those two places were here before we jump over to the returning part where we clean up the stack. And here, in the case of the base case, we set the return value. And those directly correspond to the two places that we return things in the original Java code. All right, so I hope this was helpful. The other thing you can do is you can go on the course website and download this program and actually step through it in Mars, and you should be able to see the same sequence of changes to all of these different registers and memory addresses.